So in this question, we've got a suitcase being pulled along LAX. It's 15 kilograms and it's being pulled with a force of 52 newtons at an angle of 57 degrees. So first thing we want to do is label the forces acting on this. So we know that there's an applied force. I'm going to just draw it like this, an applied force of 52 newtons. Since it's on the earth, we know there's a force of gravity acting on it, Fg. And since it's resting on the ground, we know there's a normal force. I'm going to draw this a little bit longer. And then this is the normal force. Now, is there friction or isn't there? There is an easy way to tell. In this question, it says it's being pulled at a constant velocity. And what that tells me, velocity, is that the net force, which is the sum of all the forces, has to equal 0. So there's got to be something holding it back to balance this forward applied force. So we're just going to label this the force of friction. So whatever friction is in the wheel, we'll do that. Now in this example, even though the force is being applied at an angle, the suitcase is actually moving along this axis. So we're going to keep our axis in the x and the y, so we'll keep that as the x and we'll keep this as the y. And you can see that the normal force and gravity act in the y and the frictional force acts backwards in the x. It's the applied force that we have to resolve into our components. So part of the applied force is pulling it along. So we've got the F-A-X in this direction, and then we also have the F-A-Y in this direction. So we have to do some trig on these two. So let's figure that out first. So we need to, the question is asking us to get numerical values for each of these. We know the numerical value of the applied force, but we need to know what the components are in order to break it down and find out our other individual forces. The force of gravity is actually maybe the easiest one because we have an equation for that, right? Fg is just mg. We know that the mass is 15 kilograms, so times 9.8, that works out to 147 newtons, I believe. Don't trust me. Do the math yourself. So now let's look at the components of the applied force. So first of all, Fax. You can see from the diagram that this equals Fa times the cosine of 57 degrees. And since Fa is 52, this becomes 52 cosine 57. Figuring all that out, I believe it works out to 28.32 newtons. And then looking at the y component, Fay, it's Fa sine 57, which is 52 sine 57, which is equal to 43.61 newtons. Okay, so now we have all the numbers we need and we have to just put it all together. So let's do that by breaking this into vertical and horizontal components. So let's first look at this horizontally, or along the x direction. We know that the net force in this direction is equal to 0 because of this constant velocity. So the sum of the forces is going to equal, well, what are the forces in the x? There's Fax pulling it forward, and then there's Ff in the negative direction. We can make this the positive direction, this the negative direction. So subtract Ff. So we can see that the force of friction has to equal the x component of the applied force. And we know what this is. It's 28.32 newtons, so we know our Ff. So that will give us this piece of information. So let's just write down what we know here. So this is Fg. We know that now. We know this now. We already know Fa is equal to 52. It was given in the problem. 52. And now we can figure out, the last thing we need to know is the normal force. So in order to figure out the normal force, we have to look at this vertically. And same logic applies. This is in the y direction. The net force is still equal to 0 because it's moving at a constant velocity, which means it's not actually moving at all in the vertical direction. So that means the sum of the forces vertically has to be equal to 0. Well, if that's true, then the sum of the forces, well, what are the forces? We've got the normal force acting up, so in the positive direction, but can you see there's this purple arrow also moving up. So we also have to add to that Fay, and then we have force of gravity acting down, negative Ff. The only unknown here is Fn, so we can say Fn is equal to oops, this is a mistake, I'm sorry, Fg is this in the y direction, is equal to Fg minus Fay. Look at rearrange this to get that. If I bring these two over to the other side, I get Fg minus Fay. And I can just do the math on this. This becomes 147 minus 43.61. So we get Fn is equal to, I think it works out to 103.4 newtons. And that is our last force. It's interesting to note that if this suitcase was just at rest, sitting there, the normal force and the force of gravity would be balanced, and they would be equal because they would be the only two forces on them. But because there's this applied force here, it actually reduces the normal force. See, the normal force is smaller than the force of gravity now. So not only is that applied force pulling the cart forward, but it's also picking it up off the ground a little bit. So in a sense, the suitcase is not resting as heavily on the ground. The full weight of the suitcase is not resting on the ground. So therefore, the normal force is slightly smaller than the force of gravity in this example.